In this video, I'll talk through the 2025 National 5 chemistry paper, explain how I would approach each question. Starting off in our multiple choice questions, we're asked about a newly discovered element with a predicted electron arrangement as shown. It's ending in an 8. This means it's going to be in group 8/0. How goes that? That's going to make it a noble gas. We could have used the data booklet on page 6, which shows the electron arrangements. We can see that the ones that have an 8 as their last value are in group 0. That's another way of getting to the answer as well. Everything group 1 has 1, 2 has 2, 3 has 4, so on and so forth, up until group 8/0, the noble gases, where we have got a full outer shell. Helium's the odd one out there, it's only got 2 electrons, but they all have a complete outer shell. 2 for helium and 8 for the rest of them. Next one, we're asked about the protons and electrons for iron. And how this is going to work is the atomic number tells us the number of protons. Now, in this Euclid notation it's called, we've got 2 values. The bottom number is the atomic number. If you ever forget, we can use pages in the data booklet, such as page 4. We can find iron, and we can see that it is number 26, and that is its atomic number. So if you're ever unsure which one's atomic, which one's mass, that can help us out. We have 26 protons. In an atom like we have got here, the protons will equal the electrons. The positives equal the negatives, which is why it's neutral overall. That means we're going to also have 26 electrons. That's going to make our answer C for this question. If it asked you about the neutrons, that's when the mass number would come into it. The mass equals the protons plus the neutrons. So the neutrons is going to be our mass number. Take away the protons. In this one, it would be 56, take away 26. And then that will give us 30 protons. Nope, that will give us 30 neutrons if the question asked us for that. Next question is dealing with the formula of different compounds. For A and D, they are giving us prefixes. This means that we've got phosphorus, which is P, and 3 chlorines, so Cl3. That's 1 phosphorus and 3 chlorines. That doesn't contain 3 atoms in total. Down to the bottom, carbon dioxide. That's one that you should be quite familiar with. That is CO2. That's a carbon with 2 oxygens. Now that's going to be our answer. For the other ones, they are not given. They do not have a prefix that tells us how many of each chemical we've got. We then have to use our valency crossover method. Got magnesium chloride first of all. Page 6 is going to help us out with this one. Magnesium is in group 2. That's going to make 2 bonds. Chloride is because of chlorine. That's in group 7. It's going to make 1 bond. Right, let's sketch it out just to the side. So I've got Mg with a 2. Cl with a 1. Swap them over. 1 and 2 gives you MgCl2. Our sodium fluoride is Na and F. Sodium's group 1 makes 1 bond. Fluorine makes 1 bond. And that's going to be 1 and 1. Swap them over just gives you just NaF. Now, if we look at what we've got with magnesium chloride, well, there is 3 things there. There's magnesium, 2 chlorines. Importantly, though, because it's talking about which molecules, we are looking for a covalent molecular chemical. And to get covalent molecular, that is typically when we have non-metals binding together. So although B, magnesium chloride, has got 3 things, that's 3 ions, because that is an ionic compound, because we have a metal and a non-metal together. That one. That's a wee bit of a sneaky one there, but D is the correct answer because it's got 3 atoms in the molecule. Magnesium chloride would have 3 ions in the compound, which is a bit different. Okay, next one we're asked, which of the following is never found in elements? Oh, covalent molecular, these would be your diatomic elements, which come as a pair of atoms. So we do have elements to do that. Ionic, we need metal and non-metal. You cannot have that because elements are made up of only one type of atom. We're unable to have a metal or a non-metal if you've only got one of them. That is going to be our answer there. Metallic, well, that's all the metals. Sodium, calcium and all them. Covalent networks, things like carbon, diamond, carbon, graphite, are both examples of covalent network elements. So B is our correct answer. On to number 5. We're asked to figure out which of these would conduct electricity at 600 degrees Celsius. Okay, now I'm going to see if we can use page in the data booklet to help us narrow it down a little bit. There is a page, this is the one, page 9, where they have a list of different compounds and they are melting points and boiling points. First one I catch is, well, we've got silicon dioxide is here. Silicon dioxide is a covalent molecule. Covalent chemicals never conduct unless it's carbon graphite. That for me then is going to rule out the silicon one. Lithium bromide is an ionic substance. Ionic substances conduct when molten or in solution. If we are at 600 degrees, we are above the melting point of lithium bromide. So lithium would have melted. It is ionic. It would conduct. So that's going to be the answer I'm going to go for. Ammonia is a covalent compound, so similar to the silicon dioxide. I'm ruling that out because it's covalent. Barium chloride is an ionic chemical, but it's got a higher melting point, so it wouldn't have been molten. It'd still be solid and it wouldn't conduct electricity. That's number 5 is going to be the answer of B. A little reminder, metallic always, covalent never, except graphite. It never seems to be graphite, but it could be graphite. And then we've also got ionic sometimes, and the sometimes is molten or solution. That's our answer there. Moving on to number 6. We're looking for an alkaline solution. We're also asked to use the data booklet. I usually start with the acids first of all. So the acid that I think about is going to be hydrochloric acid, which is non-metals combined together. Sulfuric works as well. Sulfuric, sulfur, non-metal. Nitric acid, nitrogen, non-metal. If we want an alkali, then we're going to want a metal oxide. If you're unsure of if there's metals or non-metals, we can use page 6, where the left hand side are metals and right side are non-metals, or you can use page number 4, which has them just with a dark line separating them, metals on the bottom and non-metals at the top. I know that calcium and nickel are metal oxides. Calcium and nickel are metals. B and C are non-metals. That's going to rule them out. To make a solution, you have to be able to dissolve. Calcium and nickel oxides, we can use page number 8 to find them. Calcium oxide is soluble, whereas nickel oxide is insoluble. Nickel oxide will leave the pH unchanged, and calcium oxide would make the solution alkaline. Next one, we're talking about adding water to a solution of acid. Acids have more H plus than OH minus, and they have a pH less than 7. Okay, so we're adding water, so it's going to become less acidic. If it's less acidic, the reaction rate will decrease. If it's less acidic, it will have a lower concentration of H positive, the hydrogen ions. It's not going to be that. The acid will be neutralized. That is when you react with a base, and that's not what's happening here because we're just diluting it. I'll pop that there. That's diluting. pH will increase. Yes, we would be below 7 and we'd head up towards 7. We can't get above 7 just by adding water, but we can get towards it. That's the answer there. Next one, we're doing a percentage by mass. That relationship is in the data booklet on page number 3. Nicely for us, they have told us that the GFM is 149. That means we'll have 149 on the bottom. That rules out both D and C. It's the mass of the chemical that we are looking at. We are looking at nitrogen. And importantly, there's a nitrogen in the NH3, but there's 3 times that. So that is the equivalent to having NH3, NH3, NH3. So there's 1 in the brackets, multiplied by the 3 means there's 3 of them. It's going to be 3 times the GFM of nitrogen, which is 14. 3 14s are 42. So it's going to give you 42 over 149 times 100. And if they wanted the actual number, you just type it in your calculator and it will spit out your answer. On to number 9. We're asked about the charge on manganese dichromate. When a chemical ends in 8, ATE, you should go to page 8 because it will hopefully be there for us. We have got Cr2O7 with a 2 negative charge. Let's start putting that together then. Well, we've got Cr2O7. That is 2 minus. Whatever it's connected to has to be able to balance out that charge. And the only way that we can balance out the charge is by this having a 2 positive charge. That makes our answer A for this question. The other thing we could have looked at is, let's just think about valencies and how many bonds things make. Well, if it's 2 minus, that's going to have a charge of 2. And we're not sure what the manganese has yet, but after we swap them over, we should have a 2 beside the manganese from the dichromate. The only way that that's disappeared is if that was also 2, because then 2 and 2 cancel down, and that leaves you with 1 manganese, and its charge has to be 2 plus, going back to the same kind of reasoning that we had before for that one. So there's 1 dichromate and 1 manganese. That means they have to have opposite charges, 2 negative in the data booklet for dichromate, 2 positive for manganese. Next one, let's go through a couple of the information we're getting told about. Number 1, we are told that it's saturated. So that means we've got carbon to carbon. That's carbon to carbon single bonds. It's insoluble in water. Now, when I'm looking at the options, I mean, propanol would be, alcohols can dissolve a little bit in water. It doesn't say how soluble or insoluble. I will go for this one though. It's got 2 carbons. Nope. It has 2 hydrogens for every carbon for that one. So, okay, if we give them a little sketch out, they've all got 3 carbons. Propane is an alkane. It has single bonds between the carbons. That ticks the saturated box. Hydrocarbons tend not to dissolve in... Hydrocarbons are insoluble in water. Ticks that box. There's 2 hydrogens for every carbon. Well, we've got C3H8. That doesn't fit the bill for that one. That's going to be incorrect. On to the alcohol. Counting the carbons and hydrogens, it's again got more than double. So we have C3H8 and an O in there. Again, that's not going to work. It'd also likely dissolve a bit in water, being a fairly small alcohol. Cyclopropane, C3H6. Single bonds between carbons. Would dissolve in water. That is going to be a correct answer. And our alkene fails from the fact that has a carbon-to-carbon double bond, and then that's going to just fold in as well. It does have 2 hydrogens for every carbon, but it doesn't fit the other criteria. Here we're given a type of chemical that you're not expected to know about, but they're asking you to figure out the general formula of it. Doing our counts, we've got C3H4, we'll get C4H6. Now what I want to do first of all is I want to check which of these would work for these 2, and then we can see if it would work for our last chemical as well. Well, Cn, so N is 3 for the first one, so C3. H is 3 plus 1, which gives you 4. That does work out. Try it for the other one. We've got C4, and then H would be 4 plus 1, which would be 5. It doesn't work for that. It's important to check it works for all the chemicals. As soon as it fails on any of the chemicals, it's not going to be our general formula. Next one, well, plus 1 didn't work. Plus 2 is not going to work either. So we'd have C3H, 4 plus 2 is 6. Doesn't match. Instantly wrong. Just double. Nope. We can see that they are not just double the numbers. 3 double would be 6. 4 double would be 8. Doesn't fit at all. By extension, it has to be the last one, but we should and will double check. You've got C3. We've got H. 2 times 3 minus 2. So C3, 6 minus 2 gives you 4. Do the same for our 4 carbons. C4 H would be 2 times 4 minus 2. 2 4s are 8, and that gives you 6. It works out. If we have C5, H would be 2 times 5 minus 2. So C5 would be 10, minus 2 would be 8. Counting them up, we have got C5, and we have got 5 at the top, 6, 7, 8 in total. That does work out. D is the correct answer. Shuffling down, we're asked about the formula mass belonging to a hydrocarbon that does not belong to the same homologous series as others. Okay, so I think we just have to do a little bit of sketching and try and figure out what this one would be. Now, something to bear in mind is that carbon is 12 and hydrogens are 1. So the first chemical can only have one carbon, and carbon needs to make 4 bonds, so it needs to be methane, CH4. And we can have wee sketches out. If you're ever unsure of how it all fit together, we can look at that. That is going to work. So that makes that an alkane. Next one, let's have a look. So we need a bit more we need some more carbons involved in this. Now I'm going to try 3. So if I had 3 carbons, that would give me 36 of my mass. Then I think if we have a single bonds to make us an alkane as well, that should give us 1, 2, 3, 4, 5, 6, 7, 8. 3 12s are 36. Add on 8 does take us up to 44. So that could or is an alkane. That means one of the other 2 cannot be an alkane. Now I'm thinking, well, we go to 4. So 4 is going to take up 4 times 12 is 48. And it's with the alkanes, it's CnH2n plus 2. So that would be C4H. 2 times 4 plus 2 would be 10. So 48 plus 10 for the hydrogens would give us 58. This is looking promising. Now, that makes me want to put D as my answer. I'd feel better if I can figure out which alkene or cycloalkane we've got. And I said that was going to be 10. That again is an alkane. So if we try 5 carbons this time, I'm going to put in a carbon-to-carbon double bond. That leaves us with 2 hydrogens on the end one hydrogen in the middle there, 2 in the next one, 2 in the next one, and let's put our 3 on the last one. That will make it C5H10. 5 times 12, 50, that's 60, plus the 10 from hydrogen gives us 70. It could have been a cycloalkane as well. Point being, it's not an alkane. That's the most important thing. The fact it's a hydrocarbon means we're not putting any oxygens in to give it any more of a mass, any heavier of a mass. That takes us to an answer D. Next one, we need to recognise our carboxyl group, and that makes it a carboxylic acid. That chops out B and D, which would be just the OH group, the hydroxyl group. Something to watch out for here is that when we're counting the carbons, we count all of the carbons in the longest chain. This would be drawn out more fully, like so, and then your 3 carbons. So 4 carbons in a row is prop. That's going to make, 4 carbons in a row is bute. That's going to make that bute and noic acid. That's going to be C as our correct answer there. If you're not very confident with your beginnings, we can go to the page 9 in the data booklet, and they have them in order of eth, meth, eth, prop, bute. Bute for 4 is the one that we are looking for. They also have bits about the naming of them over there as well, which might come in handy. Number 14, we're asked to show a different way of representing this structure. To take up the least... To do this as quickly as possible, I would probably recommend drawing out the one they give you to then compare it to the 4 that are there. The other option is to shrink these down, but I'll show you this way first. So we've got CH3. That's not shrinking it down. Let's actually do it. I said I was going to do it. So CH3. No, I'm going to draw it out. I'm drawing it out. Never mind. So CH3. Then we've got a C to a H. And then a C to an OH. I've done 1 carbon, 2 carbons, 3 carbons. We've then got another carbon with 3 CH3 groups. Now, one of those CH3 groups is going to be just through in the middle. They're kind of writing in a way that makes it look like it's not quite there. Most of the time you want to put hydrogens to fill it up, but we can't do that because that would take it away from this skeleton, from this shortened structural formula. That's suggesting there's a double bond in between carbon 2 and carbon 3. And that looks like it matches up nicely with chemical A. So problem with B is there's no carbon-to-carbon double bond. Problem with C is there's 1, 2, 3, 4, 5, 6 in a row. We should only have 5 carbons in a row. And we might actually be able to just count up. 1, 2, 3, 4, 5, 6, 7. carbons in total. Would that be a way of doing it quicker? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 carbons in C. That's too many carbons. Actually, B would have too many carbons as well. The number of carbons is not correct in B and C as well. And in the last one, there's no carbon-to-carbon double bond. We'd have these 2 extra H's, which are nowhere to be seen up in this shortened structure. If you wanted to do it the other way, which is totally fine, you just need to go through and go, right, I need a CH3, tick. I need a CH, tick. I need a C with an OH. There we go. And I need a C with 3 CH3 groups, tick. And that's everything explained. The other ones don't do that. Next up, we're talking about an alkene forming different products. Okay. So let's start off with but 1-ene. And I'm going to go against what my teachers always said about putting in all the hydrogens, because they're not actually that important here. If we have our double bond on the first, we get rid of the carbon-to-carbon double bond, and we put on 2 new bonds. So we have the bond coming off the first and a bond coming off the second. We're adding it with water. As we'll see up here, we're adding a H and an OH. And here we're putting them in different orders. If we put an OH first and an H there, that's going to give you butan 1 all. But what we could have done is did it the other way around, where we have a H there and then the hydroxyl group on the second. That will form 2 different isomers. If we make it now the 2-ene, I'm just going to move everything along. Well, this would be on the second carbon, so butan 2 all. You always go from the side that gives you the smallest value for the group. So this would also be 2 all. Both of them are the same chemical. You make only one product out of but2-ene. And that is going to be the correct answer. I'll quickly show you the other ones. So here we've got 6 carbons in a row. It was 1-ene, so it's between the first and second. We could have the 1 all version or the 2 all version. So it does make 2 different versions of it. And then the last one, for the other one, we're now between the second and the third. But again, coming off as a 2 all versus a 3 all, they would be different ones. So we could sketch them out. A kind of shorter way, seen these kind of questions before, where in the but one, we have 4, we have an even number of carbons and the C double in the middle of the chain. If it was 6 carbons and we had it on position 3, so hex 3-ene would only make 1, and you can extend that out as well for there. So very much a sketch it out will help quite a lot for a lot of people. If you can kind of picture in your head, you might be able to kind of figure it out without doing that, but that's a really good way of just kind of seeing what's going on. And this one, it's a little bit of an energy. Next one, we've got an energy question, but it's not looking like it's an EH equals CM delta T, just because we are given energies already. It's more of a scaling one. So they're telling us that 5 grams gives off 150 kilojoules of energy. And we're asked to work out it for 60. And my preferred way of dealing with these questions is try and go or get to 1 gram, what that would be, and then scale up to our, in this case, 60. We could divide 5 by 5, giving you 1. We could times 1 by 60 to get to 60. And that means we can do the same thing to the 150. You'll be, you'll have a calculator with you. You'll be able to type that in, and it gives us an answer of 1800 kilojoules. And that is answer C. Things to think about: if 5 is something is 150, then more than 5 of that will be more than 150. We could even do a bit of kind of guesstimating where, well, if you went to 50 grams, you're timesing it by 10. So 1,500 would make sense for that. We're a bit above that going to 60. So 1,800 is a bit above that value, potentially. You might have spotted you could just have times it by 12 and we'd have got the same answer. But dividing by 5 and times by 60 is the same as timesing by 12. Just depends if the numbers kind of stand out. You can see the connections between them. You might see a wee shortcut, but that would still give us our correct answer there. Next one, we're asked about metallic bonding. In dealing with metallic bonding, it's the positive metal ions attracted to the sea of delocalized electrons. Positive ions, but it's positive metal ions. That's true. There's not negative ions involved. If it was ionic bonding, it's positive and negative ions attracted to each other. So it's not going to be that one. There are delocalized electrons, and there is an attraction, positive and negatives going together for that. So actually, when I said it wasn't B, it is B, because B is the false one. It's saying which one's not involved. If the question was asking us about covalent bond, that's where there's a sharing of outer electrons. You would have an attraction between the positive nuclei and the negative shared pair of electrons, and electrostatic attraction. If it's ionic, you have positive and negative ions being attracted to each other, so that electrostatic attraction. In this one, we're trying to find a metal that could be metal X in this, based off of these results. The way it works is the further apart, the larger the voltage. When I'm saying further apart, I mean further apart in the electrochemical series. We're dealing with silver, and then the ones we are told are iron, zinc, and magnesium. Of the three here, magnesium will have the highest voltage produced, then zinc, then iron. And we can start kind of like sketching it out. So silver is going to be at the bottom. Now we can see that magnesium is the furthest away. That's good. Then we've got, then metal X. Then it's going to be zinc. And then we're going to have iron. We want something that's between magnesium and zinc. Is there any options? Magnesium and zinc. So aluminium is our only option that we've got. That means aluminium, and it's first one. Lovely. That's going to be our correct answer there. Sodium is higher up than magnesium, so it would produce a larger voltage than magnesium one. Nickel is closer to silver, so that'd make a smaller value than iron, and copper is even closer again, so it'd be an even smaller value. So the further apart in the electrochemical series, the higher the voltage that we'd produce. So it's just trying to get a head around that. They've put it not in ascending order of voltage as well, perhaps deliberately, perhaps not, but that's what would pick up the mark for that one. Number 19, we're looking for something that's not a redox reaction. Okay, so redox is when we have oxidation and reduction. And based off of oil rig, we have oxidation is loss, reduction is gain of electrons. So the zinc has lost electrons going from Zn to Zn2 plus. It's lost electrons, which means it's been oxidized, whereas the hydrogen ions have become neutral, so they must have gained 2 electrons in that one, and that's going to be a reduction there for that. The copper is virtually identical to the zinc above. Chlorine is gaining electrons to become chloride ions, so that is going to be a redox reaction. The iron here is becoming more positively charged, so it's losing an electron to do that, whereas the bromine has become bromide by gaining electrons. The only thing that's happening here is it's going from a solution to being solid. That suggests we've evaporated off the water. And that's not a redox reaction. So the charges and everything haven't changed at all. D is going to be a correct answer there. Which of the following would be recovered unchanged in the Oswald process? A catalyst speeds up a reaction without being used up. There's 2 processes in the fertilizers topic. There's Haber process, which has an iron catalyst, and Oswald is platinum. That's going to make our answer D again for number 20. All of them are all reactants in that process. They are getting used up. You would not get them back unchanged. They're going to be in the product of nitric acid. Number 21, we're talking about a proton. Proton is just a positive charge. It has a mass of 1 and an atomic number of 1. That's going to make our answer A for this one. That makes the answer A. Protons are what are responsible for the atomic number. They also have a mass of 1. And simply, Precipitation is when we produce an insoluble product from a mixture of solutions. So insoluble. And we're just asked which can be prepared from it. So we're just looking which of them is going to be insoluble. So it's sulfates, lithium, sodium, barium. We're asked about lithium, sodium, barium, and magnesium. Odd one out, barium. Barium is going to be our correct answer. That gives us C for this one. Number 23, we're asked to read off of a pipette or a burette in this question. Very similar question, was actually in the higher paper as well. I just finished going through. We need to remember to look at the bottom of the meniscus. That's dealing with the bottom of the sort of bubbly part that's at the surface of the liquid. Bottom of meniscus. Correct volume. So running over here, where are we? So get your bearings. What we can do is look halfway between the two. It would have to be halfway between the numbers. That's 9.5. Every little indentation, every little line is going to be 0.1. So starting at 9, 9.1, 9.2. We give us an answer there. Or we could count backwards from 9.5, 9.4, 9.3, 9.2. Hopefully you've had practice with doing that in class during things like titrations. Just make sure bottom of meniscus and read it off nice and carefully. Next one, we're asked about concordant results for National 5. We are looking for values within 0.2 centimeters cubed of each other, regardless of if it's titration 1, 2, 3, or 4. We are just looking for the ones that are in close agreement with each other. There might be a situation where all 4 of the values are within 0.2 of each other and we average them all, or it might be in this case just a couple of them is picked out. So titration 1 we're ignoring because it's over 0.2 away from the others. Similarly with the titration 3, it's too far away. Taking the average, we add them together and divide by the number of values. In this case it's 2. It's going to end up halfway between the two of them. That'll give you 10.2 as your final answer. An average should always be between the two values or between the largest and smallest values that you're averaging. If you end up with a number that's bigger than 10.2, it may well be that you've not entered it into the calculator properly. So either using brackets or fraction button will help get the correct value. Last question of multiple choice. Most appropriate for 10 centimeters cubed. Measure and transfer. Well, a pipette is what we would use in those ones. Conical flasks are where we would carry out the experiment. Measuring 10 centimeters cubed isn't going to be done as accurately by a measuring cylinder. Burettes are good at measuring out volumes, but it's the transfer part that's leading me to the pipette as my answer for that question there. Moving on, we're asked about testing for hydrogen gas. There are 3 gas tests that we need to be aware of. So hydrogen burns with a pop or a squeaky pop. I'm sure you get them out with just a pop. I was taught with a squeaky pop and I'm sticking with it. The other ones would be carbon dioxide, turns lime water cloudy, and then oxygen relights a glowing splint. Next one, for a bit of a change here, we're asked to dissect someone else's diagram, which if you're as unartistic as I am, is a blessing that we don't have to draw them out. What are some of the problems? So let's go through the checklist that we would usually do. So number 1 would be thinking of the gas. Would the gas go into the delivery tube? Well, some might, but some might escape. So we are missing a stopper, or a bung, as some people say. So no stopper on the flask. What else do we have? Let's follow the gas through. We could go down here. Up we go. Oh, look at the end. We have got a line. We have a blockage. They've accidentally closed off. That is our delivery tube. So the delivery tube is blocked. I'll just say at end. They'll know what they're talking about because they're the ones that came up with this. Block that end. Another thing is, it's not just to collect it, we have to measure it. How would we know how much we've got when the measuring cylinder isn't graduated, doesn't have the lines on them? So no graduations are the little lines that tell you how much we've got. So no graduation marks on measuring cylinder. Why is it a measuring cylinder if it's not got the measurements on the cylinder? Last up, labels on everything except that. So the measuring, it doesn't measure cylinder. So if at any point in this paper, still to come, we get asked to do a diagram, we would have to try and make sure we don't fall into those mistakes. Next one, we're trying to get a dry sample of the zinc sulfate. And this actually ties into the multiple choice one. Yeah, this is a lot further back than I thought. Where was it? Was it multiple choice? So this is going back to question 19. Our correct answer was the one where we are driving off water. We are carrying out an evaporation. The technique would be evaporation. Not burning it. You could talk about heating it, but we want to drive off any water that was there to have it as a solid sample. Next, we're asked about a graph, and we're asked about the average rate. Data booklet says average rate is changing quantity over changing time. What I'm going to want to do first is I want to just look at the two values we're dealing with. So the first 50 seconds, we're at time 0. So it's going to be at 0. And then after 50 seconds, we're up. I'm just trying to get this as bang on as I can. Now, our final answer is going to depend on where we're taking that line to be. How wide an ink we're using, or how wide a pen we're using. We are somewhere between 88 and 86. Now, is it quite 87? I'd probably go 87 because it's kind of part way, well, it's like almost halfway between. I'm going to go for 87. So we're starting at 0 and we're finishing at, I'm going 87. So that's a difference of 87. It's taking 50 seconds to do that, from 0 to 50. I'm going to plug that in my calculator, and I get 1.74 centimeters cubed per second. I've just double checked the marking scheme to see what range they're accepting. So they're accepting 86, 87 or 88 divided by the 50. So you have a wee range of, using the different values, we could go from 1.72 up until 1.76. So I'm slap bang in the middle because I took the middle value. If you went a little bit higher, you'd still be okay. A little bit lower, but it'd have to be numbers between 88 and 86 because of where the line's sitting. For that one, add a curve, lovely, to the graph to show the results that expected if it was repeated with the same mass of lumps. Lumps have a lower surface area. Lumps would react more slowly. What we're looking for is that your graph curves less steeply, and it finishes at a later point. So our original graph is finishing roughly about 80, I would say. My one's going a bit past that in there, and that would be our correct answer there. Okay, next one's asking about the volume of product that would be formed in a different reaction. As it stands, on the original experiment, we got 96 centimeters cubed. That was using sulfuric acid, and we are this time using hydrochloric acid. Okay, formulas, let's think about them. Oh, it tells you, lovely. So, what's one of the main difference in terms of how acidic it is that we have twice the number of hydrogens in the sulfuric acid than the hydrochloric acid. Because we're making hydrogen gas, if we're using hydrochloric acid, we have half the H+, therefore half the hydrogen that we'd make. If it was 96 on the first one, we would have 48 centimeters cubed, so half of the original value. Here we're asked to draw the diagram for oxygen. In dealing with oxygen is in group 6. It means it has 6 electrons in its outer shell. What that means is oxygen has to make 2 bonds, and in this case it's going to make 2 bonds to itself. So oxygen exists as a diatomic molecule with a double bond between the oxygen atoms. In these diagrams, every line, every bond is represented by 2 electrons. That's 2 dots or 2 crosses, however you're doing it. Now, when we're overlapping our oxygens, we're going to have 2 electrons from the first one. Now, I the dots and crosses so we can see them separately. And then each of them would still have 2 pairs of electrons that are theirs alone. But by sharing those 4 in the middle, we then get the full complement of electrons in the outer shell. Makes it more stable. Put the oxygen... O for oxygen, and that would be our correct answer. Next one, similar chemical properties is suggesting they're in the same group. That is group number 6. So sulfur would be my answer, but we could have any of the other ones: selenium, tellurium, or polonium. Let's just put them in. Next up, we're asked to talk about the relationship between temperature and solubility. As temperature increases, solubility is decreasing. It's important to do it cause and effect. The temperature affects the solubility, and that's why that one's written about first. This shape, 4 shapes that we need to know about. We have got linear, we have got angular, which is our answer here. We have trigonal, pyramidal, and we have tetrahedral. Next one, talking about covalent bonds. I mentioned this earlier. We have got an attraction between the shared pair of electrons and the positive nuclei. So what we down, circle them. So the positive nuclei are held together by the common attraction for shared pair of electrons. Plastics and polymers. We are given a repeating unit and we want the monomer. All we have to do is fold in the arms to make them a double bond. It's going to be addition polymerization we come across, and that's where we have something, an unsaturated substance, so it needs a carbon-to-carbon double bond, and then at the top we just copy what's there. The H's all the way around would pick up that one. Data term, a molecule with only 2 atoms. That is a diatomic molecule. Complete a graph. Because we've got words and numbers, we're going to want bar chart, and we're doing miss a big box, then do a big box, miss a big box, do a big box. Let's see how we can get on. Okay, first going to check what each bar box would be worth. So a couple of ways that we can just practice check numbers to see what we're going up in. But for this one, I think it's going to be a little bit odd. So 80 of a 80 degrees is 5 little boxes. So 80 divided by 5 means every box is 16 for that. Now that's going to get a little bit awkward, I would say. Oh, hang on a minute. Feel like here I've done my wee skippy thing. Because you would have been told to make sure that all your jumps are equal. So I feel like they should have started at 80 there. Or are we using that kind of break thing? Okay, I was thinking that makes the numbers awful. So let's go again and say, well, let's go from, we've got 2 numbers. So here it's 20 of a difference. So if it's 20 of a difference for the 5 boxes, every box is 4. 84, 88, 92, 96, 100. That makes more sense, right? Okay. Where am I going to for POM? POM is 165. See, that's still not that great, is it? I feel like we should have picked better numbers. Okay, so POM 165. Okay, so we're at 160. That'd be 164, 68, 72, 76, 180. So we are allowed to be half a box out. So it's half a box tolerance. It's described as. So although I'm at 164, because each box is worth 4, half a box would be 2. So that should be okay for that one. I just wish it was sitting nicer on a number and maybe made that numbers go up. So you got each box was 5 would make more sense maybe. 260 right to the top. No arguments with PET. PET. So start bottom up to very, very tippy top, along and down like that. Next up, HDPE 131. We're at 120, 24, 28, 32. That's as good as I can get it. 82. Is it PVC? Yeah. So there's 80. 84. So I'm trying to go, let's go half a box up. And there. Last one of PP 130. So 130 is halfway between 140 and 120. So 1, 2, 4, 2, 8. I think the best I can, if I can, put it halfway up. So it's kind of 2.5 boxes if it will let me. And then hopefully something like that will pick up the mark. As I say, I'm not too keen on the scale that was chosen, but it is what it is. Moving on to the next one. Why should it not use as a container? Presuming it's got a boiling point less than boiling water. Water boils at 100. It would have melted at that temperature. So the PVC would melt if we used it. Okay, this one we're asked about compounds that contain carbon atoms. Now, this is something called a benzene ring. We don't have to know about that at this level. This is a bit of a question that's been dropped down from advanced higher chemistry. Dealing with a problem solving one. So name the functional group that's present in both the L-dopa and ibuprofen, but not in dopamine. So it's in top and bottom, but not in the middle. For that. So things I'm looking at, so let's deal with this, like benzene ring. Well, that's in all of them. So it's not going to be that. They too have hydroxyl groups and the bottom one doesn't. We're not asked about that. We have NH2s in those ones. Nah, not that. So the only thing the first and the last have that the middle one doesn't is a C double bond OOH. It says name it. We have to give the name of it, which is a carboxyl group. We're not drawing it out. We're not circling it. We're writing a carboxyl group. Name the addition reaction that involves the addition of hydrogen. That is hydrogenation. Carbon to carbon double bond breaks and hydrogens are added. If we have water added, it would be called hydration. If a halogen, which is group 7, it's halogenation. Hydrogen hydrogenation. A catalyst is a substance that speeds up a chemical reaction without being used up. Next up, we're asked about something called a chirocarbon. This is very much from advanced higher chemistry, except they don't get told, and it means it's attached to 4 different atoms or groups of atoms. As we have there, identify the chirocarbon in the ibuprofen. So first carbon has 3 H's, can't be that. Second carbon, what does the second have? It has a CH3. That's another CH3, a H, and then all of that. That is not 4 different things. There's 2 hydrogens on the next one, it's not that. Benzene ring, that's not going to have it. They have not got enough bonds that are both vacant to carbon. It's not going to be that one there. This one has 2 carbons to oxygen. Can't be that one. This is the only then last remaining option is the carbon there that I've circled. How's that? Well, we've got a methyl group CH4. We have a carboxyl group COOH. We have got a hydrogen. And we've got all of this as well. So that makes that the carrier center, that one. I'll do a similar colouring in here. That would be one group. They have an NH2. This one has an NH2, a hydrogen there, and then again the carboxyl group as well. It's 4 different atoms or groups attached to that carbon. That is the one we've got there. Again, okay, so again I dropped down. Also in higher human biology, antagonist works by blocking the body's response to pain. Name a medicine that could be described as an antagonist. Pain. Ibuprofen. And that might have been a medicine that you've came across and you had a headache or tooth pain or anything like that. They might have recommended ibuprofen to take. So ibuprofen. That's an answer there. Moving on. What is meant by a fuel? One of my favourite definitions. A fuel is a substance that burns to release energy. With a lot of these definitions, just saying it again and again and again and again gets it stuck somewhere in your brain so that when it comes up, we can pick up a nice straightforward mark. That is a substance that burns to release energy. A fuel is a substance that burns to release energy. It's a substance that burns to release energy. It is a substance that burns to release energy. We have to draw out the full structure of this chemical here. We have got something, pent. Pent is 5. We can check in the data book if you're unsure. Single bonds between the carbons because it's N. We have got 3 groups. We have 3 1 carbon groups coming off the second, and the 4th of something like that. And then we can just pop in our hydrogens. We could have done the flip, reversed side of it. Now with the methyl groups, I'm just going to write them as CH3s, partly for space. Partly because I can't, partly for space. And then we've got our other H's go on there as well. We need to put in all the H's that we've got. You're allowed to have a mixture of shortened and full structural formulas. If it said full structure, I would have to make sure I put in all the H's around my methyl groups, but I'm okay here with this one. Next up, we're told about how we can make it, and we're asked how we can tell these two things apart. Bromine solution decolorizes when we add unsaturated chemicals. They're the ones with carbon-to-carbon double bonds. So isobutene will decolorize bromine water or bromine solution. One day I might accept that solution seems to be the more common word that's used, but I'm sticking to the water, and I'll just put in the other one. Will not. Yeah, shuffling on. State the effect that increasing the number of branches and alkanes containing the same number of carbon atoms as in the flashpoint of the alkane. Okay, so we're looking for total number of carbons then. It's not number of carbons in the chain, it's number of carbons full stop. So hex is 6, hept is 7, oct is 8. Pent is 5, 3 ones for that would also give you 8. Hex is 8, 9, no, hex is 6, 7, 8 for that one. Hept is 7, plus 1 is 8. So we can go from octane to the methylheptane to dimethylheptane to trimethylheptane. So as number of branches, now I'm not going to write the whole thing of like branches and alkanes containing the same number of carbons. I'm just going to say as number of branches increases, flashpoint decreases. So I'm just answering the way they've worded it there. They could have talked about it being how easy it is to catch it fire to it. So if the question was talking about how does the branches affect the flashpoint, or no, affects the ease of the flammability, that's what I'm looking for, the flammability of the chemical, well then it's going to be getting more flammable because it catches fire at a lower temperature. Anyway, this one doesn't, so we just need to say them for that. Let's predict. This is how many carbons? 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I would be looking at these ones here. So we're going up by 18 by adding a carbon. We're then going up by 17. So I would probably suggest running up by 16, 29. There'll be a bit of wiggle room. I'm going to go 29, just presuming that we're going up by the same every time. Alcohols are added, oxygenates. Why did it help Patrick to burn? Because it's got more oxygen and it needs oxygen for complete combustion. So they ensures our chemicals fully burning. Why does ethanol have a higher boiling point than methanol? Ethanol's got 2 carbons, it's a bigger molecule. And then when it's to do with boiling points and melting points, we're talking about intermolecular forces, the attractions between the particles. So it's a large molecule and has stronger intermolecular forces. Describe the chemistry of fertilizers. Okay, so first thing we could talk about is that so they contain NPK. So a fertilizer's got to contain nitrogen, phosphorus, and or potassium. Fertilizers are spread onto the soil and get into the plant through the roots, so they must be soluble in water. Now, maybe a couple of example, or an example might be, so aluminium phosphate has phosphorus but is insoluble, whereas ammonium phosphate has nitrogen and hydrogen and is very soluble for that. So aluminium. Ammonia is an important chemical for fertilizers made in the Haber process. It's a way of getting nitrogen into the soil. It's a reversible reaction. It's a reversible reaction between nitrogen and hydrogen, and it provides ammonia for that. We could add in the formula equation and the balanced equation showing this reaction that's happening as well. Mentioned it in the question about Oswald process. It involves use of an iron catalyst, which speeds up being used up. Ammonia can then be used in the Ostwald process to produce nitric acid. So ammonia is reacted with oxygen and water to produce nitric acid. Platinum catalyst this time. Partly to get it stuck in your head, hopefully it speeds up the reaction without being used up. That can then be used in a neutralization reaction to form soluble salts that can act as fertilizers. Bases include metal hydroxides, oxides, and carbonates along with ammonia. You could include an example reaction, so nitric acid and potassium hydroxide. Acid plus base makes salt and water, potassium nitrate. Potassium nitrate provides the potassium and nitrogen, or ammonium phosphate, phosphorus for that. So I'm picking specific neutralizations that happen. Got that. Something I just thought we could add in is the reason that a nitrogen is turned into ammonia to then be able to get it into the plants is it's very unreactive. It's N2 and it has a strong triple bond between the atoms and it makes it very unreactive. So we can't just add it to or react it directly with chemicals to be able to get it into the plants. Its inertness, its inactivity, its unreactiveness is why it's used to preserve. It's used as a gas and in like packaging like crisps and things like that because it's not going to react with the food. It's not going to cause it to go off for that. Pretty happy with that answer there. I can't think of anything else that I could add in. It's 1 mark for being limited, 2 marks for being reasonable, and 3 marks for being good. This is going to be worth all 3 of the marks. I've gone above and beyond. You don't need all of the things I've put about. You don't need everything I've put to get the 3 marks, but this is everything I can think of. There might be stuff I've missed, but that's where I am just now. Moving on, we're talking about radioactive decay. This is when the nucleus of the atom breaks apart. That's why it's nuclear chemistry. Next one, we're asked, name the other elements. So, apart from phosphorus. So, we have sodium, we have hydrogen, phosphorus has already been mentioned. 8 means there's also oxygen present in the chemical. If it ends in 8, go to page 8 and that will show you for itself. It will show you there's oxygen present as well, but that would pick up that. We don't need to write phosphorus because it says name the other ones. I don't think it would negate it. I don't think you would lose a mark if you did, but just those 3 are what we're looking for. Half-life is unaffected by the usual type of things that affect like rates of reaction, stuff like that as well. So the try trick is it stays the same. That's why when there's been a nuclear disaster in places like Chernobyl or Fukushima, then the chemicals can't be made to break down any quicker. It's one of those things that can only contain them, and then just naturally over time it'll start to break down, but it does take lots and lots of years, especially with isotopes with a longer half-life. Here we need to figure out what's missing in the relationship. So the mass numbers will need to equal each other. Left hand side versus the right combined. Well, the mass hasn't changed, so 131. And we're looking for a number that when you add on -1 gives you 53. So because they're on the same side, I'm going to say it should be 54 because 53 equals 54, add on -1, which same as just take away 1. So then I just need to find out which element is number 54. Is little data booklet going to help us? It will. That looks like xenon, 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 xenon. It says name, so I would put the name. They're usually quite flexible and let you put symbols, but it says name, so name it. Next one, we're asked about the half-life, and to set this up, we're going to look at, need to know something at the start. The end, we have our total time, and then we have the time for the activity to half, which is the half-life. Right, what are we told? Sample had a mass of 40, that's at the start. After being left for 32 days, that's the total time. It had a mass of 2.5. At the end, it was 2.5. And the way these questions work is that every half-life the mass or the activity will half. So we've halved the first half-life. We then get down to 10. We then go down to 5. And then we go down to 2.5. Now, importantly here, for our count of our half-lives, is how many arrows there are. So we've halved it once, twice, 3 times, 4 times. And what that means is, let me just get rearrange this for a wee bit of space. So 4 half-lives was 32, or is 32 days. So 1 half-life equals, well, to go from 4 half-lives to 1 half-life, divide by 4, do the same to the 32, and we get 8 days as our correct answer. Next, we're asked to label and scale our chemicals. Okay. So, what I'm seeing here, so this will be number of, oh, so it's a different chemical, right, that's important. So it's a half-life of 5 years. So we're dealing with time, 20 units, so that'd be in years, because it's in 5 years. Well, if it's a half-life of 5 years, then after 5 years, we'd be at half of what we started. We're starting 100%, after 5 years, we would be at 50. So then every big box in the bottom has to be another 5 years. I'm liking this more because we're starting at 0 and it's all sitting quite neatly and tidily. So 40, 50, no, 45 and up to 50 for that. Now, to double check that, if I'm right, well then at 10 years, we should be at 25 because it'd go 100, 50, 25, then 12.5. That is, with my wiggly line, 2.5, give or take. And then, if I was to go another 2 years, so another 5 years, sorry, I was going another 5 years to here, we are at just about 12 and a bit, so 12.5 looks right for me. So I am happy with that one there. So we're getting 1 mark for putting an even scale, going up in 5s from 0, and then also having time in years. So labels in units is what we'd want for that one. State the meaning of the Latin term moles. It'll tell us in here. State the meaning of the Latin term moles. Latin term for mass is moles. So mass. That was felt like it was going to be more difficult than that. Fair enough. Nuclear notation for Avogadro's constant. Okay, so this is where we have the mass number, the atomic number, and the symbol. Now, I know it's off a carbon, and presume it's going to tell us up here. Took this one former, number of moles of carbons and 12 grams of carbons, where each atom contains 6 protons and 6 neutrons. So to get the atomic number, it's the number of protons. That's going to be 6 at the bottom. It's carbon, so it's C. It's 6 carbons and 6 neutrons. They're in the nucleus, that's the mass, 12 is the mass. It was that chemical that Avogadro did his experiments on to figure out how many atoms are in 1 mole of this substance. And that's where we get this big massive number of 6.02 times 10 to 23. Calculate the mass in grams of this number here, 6.02 times 10 to 23 molecules. Now, looking like it's feeling like it's going to get a bit complicated. It's not actually that hard with this question because it tells us that 1 mole contains that much. So we are just asked for the mass of 1. We're actually just asked to figure out the mass of 1 mole. From the data booklet, well, number of moles equals mass over GFM. So number of moles, nope. So mass equals number of moles times GFM. So mass equals 1 times. We've got 2 hydrogens and 1 oxygen. That's 2 and 16. They're not ones that you have on the top, off the top. If they're not ones that you have off the top of your head, we can use page number 7. Let's find hydrogen. There it is there. It's a 1. It's the first number. And then oxygen 16. There we go for that. So that gives you 18. 1 times 18 just stays the same. So it's going to be 18 grams as an answer. So they've put this here and it's looking quite scary and quite big. But they're already, but they tell us above that that's what we've got to use. Explain why the number of electrons was not considered when calculating the mass. they have a mass of around 1/1000th of a atomic mass unit. They're teeny totally. We ignore the mass. They have very little mass. Negligible is a word we use, or they have no mass. So they have. Let's go no to both. Don't think teeny tiny is the word I should be using here for that, but they're very, very small and very little mass to come with it. Calculate the table for this. Okay, so total number of atoms in a molecule. There's 5 things, 1 carbon and 4 H's. So that will be 5. And then doing it off what it's in here, we just put L on the end. So L is this big number here, the 6.02 times 10 to the 23. So we just need to put 5 L. So I'm only seeing that because that's what they have done up here. What I wouldn't have, if I hadn't went back and checked that the table was already there, I would have been writing that we're doing what's 5 times the number that L is. So L is 6.02 times 10 to the 23. So I would have ended up putting 6.02 times 10 to 23, which would give us so I would have written 3.01 times 10 to 24. I just feel like that, again, I'm being maybe a bit critical here, but to make sure we knew that we're just to follow this pattern, having it that way would have just, maybe that's, they're thinking is that's too easy. So it might have made it easier for us just having it in I line. Never mind, let's just chop that there. Moving on, we've got 2 possible structures. If they have the same molecular formula but different structural formula, they are isomers of each other. Draw and name one of the isomers. Oh, that means I have to draw both, doesn't it? Okay, so we've got 3 carbons. We've got an OH group. Now I could put the OH group there, or I could put it in the centre. We want to make sure that our oxygen is what's connected to the carbon. It's going to be propan. It's in the second carbon, so 2O versus propan 1O. If we were to have it on the one on the right, like so, that is still propan 1O, because with number from the side that gives the lowest value, we'd number from the right in that case. So that would still be the same. If you're needing or looking for a little bit of assistance with the naming of those, in the data booklet page 9, they give us the 2 isomers there with the 1O showing where the OH group would be. Want to balance this equation. Let me just duplicate it so we can look. Okay, so what I'm going to do first, I'm going to do the carbons first. We have 3 carbons on the left, 1 carbon on the right. Let's put a 3 in there. We have got 8 carbon. We have 8 hydrogens there, 2 on the water. Let's put 4 of them. Now it comes to the oxygens. So I've got 1 oxygen there and 2 oxygens there. I've got 3 times 2, which is 6, and 4 times 1, which is 4. So I've got 3 and I've got 10. Now I don't want to put anything in front of this one here, because if I was to change that to get more oxygens, I'd have to fix this, and it would just all go in a cycle and would be absolutely, we'd just keep going around in circles. So I'm trying to think of a number. I need to make up the rest of the oxygens using the O2, because that only affects it. Now, putting a 2 there is helping a little bit. Putting a 3 there, we're now at 7. Putting a 4 there gets us to 9. And this is where, for easiness, I am going to, or what we could do, is keep in, well, if we had 4.5, 4.5 times 2 would give us 9, and then we'd get 2, the same number on each side. Now, personally, I don't like that. There is a time, a different course in higher chemistry, where we're restricted in a certain way, it just looks weird to me. I'm not the biggest fan of it. So what I would do instead, just to make me feel a bit better, is I would, after we've got numbers that work, is I would double them up to get whole numbers. And we're allowed to have correct multiples. So if we double up everything, that'd be 9, 6, and 8. We have got 6 carbons, all good. 2 times the 8 is 16, so it's 16. And then we talked about the oxygens, we'd have 2 and 18, so 20. 6 and 2 is 12, plus the 8 is 20 again. Now, we're getting a bit big, so I'm not sure I even like this way that I've done it, because we've now got quite large balancing numbers. But you are allowed correct multiples of them. Just sometimes we might be better off using the halves and things like that, just to make it a wee bit more straightforward. But that would be answers there. A draft shield prevents the loss of heat to the surroundings. And next one, calculate the average temperature for the 3 experiments. So this isn't to do with the concordancy. They're telling us to take all 3. So 23 and 20 and 20. Divide that by 3. Gives us 21. And we're using that to calculate the average energy absorbed. Data booklet says that EH equals CM delta T. EH is the energy released, which is what we're trying to work out. C is the specific heat capacity of whatever we're heating up. It's water in this question, which means it's 4.18. If it was a different chemical, they would tell us that in the question, or that's what we would be asked to work out. It's the mass of the chemical being heated. It's 100 centimeters cubed, which is equivalent to 100 grams, which is equivalent to 0.1 kilograms. As a check, if you look at the value for specific heat capacity, kilojoules per kilogram per degree Celsius. So that's kind of a clue that we need to do that. And then we worked out it was 21 degrees was our temperature change. 4.18 times 0.1 times 21 gives 8. In a calculator gives 8.778. I like 3 significant figures, which would be the first 8 and then the 7. I would then want to round this up, because so if I want to end at this point here, I'll look 1 past and see does it round up or round down, and then that'll give me 8.78. Describe liquids like water in which substances dissolve to form solutions. That is going to be our solvent. When it comes to solutions, the solute is what is dissolved. The solute is what's dissolved. The solution's what formed, and the solvent, as it says, is what's used to dissolve it. When we're naming a monomer, just drop the poly. Instead of polyethanol, it's just going to be ethanol. Why is ethanol not used in an addition reaction? It is saturated. It does not have a carbon-to-carbon double bond. Or that one. Next one, we're doing a titration here. Oh, that's a question. Titration. We have an acid in a conical flask, and we're dripping in with the base, sodium carbonate. Let me just pop that in there. Base, acid. Why is an indicator? It lets you see the end point. It lets you know when the reaction's finished. It lets you know when to stop adding. So to see end point, or to show reaction is complete. Next one, we've got a 3-mark titration question. First thing that we want to do is to decide on the 2 chemicals we're talking about. There are only 2 chemicals shown. It is going to be those ones. We're asked to calculate the concentration of the hydrochloric acid, so we deal with that last, which means we're going to start with the sodium carbonate. It's going to be N equals C times V. Another thing you can do to see which one to start with is look at what information we're told. We're told the concentration of carbonate is 0.1. We'll pop that in. It's moles per litre. So we should change this into litres by dividing by 1,000, which would be 0.019 litres. I'm going to times that by 0.019. That's going to give me 0.0019. Ratio, it tells us, is a 1:2 ratio, which means we have to double it up because we're going from 1 to 2, so we can times by 2. And that'll give you 0.0038. And then we're asked to work out the concentration. If N equals C times V, you think of it like that, it's going to be N over V for concentration. So C equals N over V. C equals 0.0038 divided by 25 centimeters cubed, or 0.025. Again, just divided by 1,000. And then final answer, 0.152 moles per litre. Okay, another aside time. If you choose never to change them into centimeters cubed, nope, never to change centimeters cubed into litres, questions like this, it'll work out. So we would have times it by 19, we would have times it by 2 to double it, and we would have divided it by 25. And that's fine. Problem comes if the question, as it sometimes does, goes, I want the moles, I don't want concentration at the end, or I want the mass at the end. Your answer will be 1,000 times too big, and it will not give you the correct answer at the end. So in that situation, people are making 2 mistakes by not converting, but they cancel each other out, which is fine. To make sure that's not going to be a problem, that's why I'm very insistent that we should turn them into litres, divide by 1,000, and then that makes sure, even if it deviates from a moles concentration volume straight through to moles concentration volume, we are still in a position to be able to carry it out correctly. Name this salt. The first part comes from the base, and it's going to be the lithium. And then the second part is going to come from the acid. And instead of nitric, we put nitrate. So lithium nitrate. Now I just realised that we've actually got that here, don't we? We have our base, acid, salt, and water. Li for lithium. Nitrate is on page 8, and you can actually see that NO3 is nitrate. So you could use that page if you're not quite sure of the naming scheme for that. A little bit here, well, lithium's in group 1, and NO3 1 minus makes 1 bond. That's why it's LiNO3. That's how they kind of fit together. Whereas when we're dealing with the oxygen's in group 6, so makes 2. So when we swap them over, that's why we get the formula that we've got for that one. This one, we are asked to work out a number of moles, and actually this is a really good example of where not converting into litres will cost you a mark. So final thing they want is the mass. Well, I know that we're dealing with N equals M over GFM because we're asked about mass, and mass equals N times GFM. Now we don't have a number of moles, that's concentration, watch out for that. But we can work out how heavy 1 mole of lithium nitrate will be. Got lithium and oxygen. So lithium is, we've got lithium is a mass of 7 and oxygen is a mass of 16. Quite a common one to come up used. So we've got 2 times 7 and 16. So 14 and 16. That'll give you 30. So that's going to be something times 30. Don't have a number of moles, but we do have concentration of volume. So we can work out the number of moles. It's 0.5 times 0.25, 250 divided by 1,000. And that will give us 0.012, nope. That will give 0.125. And then we can plug that in over here. Times that by 30, it gives 3.75 grams. If someone had done 0.5 times 250, that will give you 125 moles. Then 125 times 30 gives 3,750 grams. So that would be claiming that in a volume less than a can of juice, we would have 3.75 kilograms of substance in it. So a kilogram bag of sugar, the kind of typical normal size bag of sugar, is 1 kilogram. So 3.75 of them in less than a can of juice is not going to work. It's why we need to turn it into litres to make it all work and flow together nicely. Moving on to another neutralisation reaction. Looking for the missing chemical. And what I would start to do is let's cancel out things that are already there. So sulfate and sulfate. Hydrogen and hydrogen. Ooh, missing 3 oxygens. What have we got? We've got CO3. CO3 has oxygen. That will be in group 8. It is carbonate. Let's prove it. CO3 2 minus carbonate. Cu is for copper. That means we're going to have copper carbonate. And that is our answer there. Now, what's other approaches we could take? I mentioned earlier about the different types of bases. So bases could be metal oxides, hydroxides, and carbonates. Or ammonia, which isn't going to be in this case, because there's no nitrogen at all. So it's going to have to be one of them. The fact that we're making carbon dioxide, carbonates make carbon dioxide, I suppose we could do it that way. But also the letters would all kind of work out together to tell us it's carbonate. Term used to describe reactions that release heat energy. Heat is escaping, it's exiting, it's exothermic. Endothermic absorbs heat. So it's going into the substances and pulling it out of the environment. No, don't say that. Don't say that. Okay, so here they're giving us something from higher chemistry now. Aren't we just the luckiest? We have got something called the activation energy of EA, and we've got the enthalpy change. Calculate the enthalpy change for the reaction below. So enthalpy, it says, is delta H. That's between our two platforms. From there to there. Now, the way I would do this is, it is a difference of, well, it's 150 take away 50, so 100. And if we look at the shape, it fits better with the one on the right because we're dropping from the start to the end. And that means we're doing a negative enthalpy change, it's called. So it's going to be minus 50. Nope, that's a lie. It's going to be, in our one, minus 100. So minus 100 kilojoules for that one. Next one, we're going to use the val. So we need to keep looking back at the previous graphs. Now, a catalyst is lowering the height of the peak. If we're looking over here, the height of the peak is to do with the activation energy. So it lowers the activation energy, decreases the activation energy. Enthalpy change is the distance between our two platforms, as we've got it labelled and as we calculated. That's not changing, and that has no effect on that. That's something that if you move on to doing higher chemistry, that's the definition that starts to get used there, that a catalyst lowers the activation energy rather than speeds up a reaction without being used up. Okay, so in this question we're looking at different metals and how they react with different chemicals to place them in some sort of order. What we could do is make up an electrochemical cell where we've got the two metals connected by a wire and dipped into an electrolyte. That could be something like sodium chloride solution, some sort of ionic solution. The electrons flow from the more reactive to the least reactive metal, from high to low in the electrochemical series. And also talked about before, the further apart, the larger the voltage. If you can connect different combinations of the metal and record the voltage produced, that will give you, and look at the direction of flow, you can get an idea of it, of this one's higher, this one's, if this pairs further apart or close together, and which one's higher and which one's lower, would start to help with that. We could also test them with water. reactive metals like calcium will react with water to give hydrogen. The other three wouldn't. So metal plus water makes metal hydroxide and hydrogen. Calcium and water would make calcium hydroxide, just as an exact example. We could also test it with dilute acid. Acid plus metal makes salt and hydrogen. A little bit different from a neutralization because there's not water we're making, it's hydrogen. Here I've added in about using equal masses and volumes and concentrations to make it a fair test, and how fast the bubbling gas is produced gives an indication of the reactivity. Again, calcium would be the most and copper would be the least. Shuffling on to another reaction that can happen is that they can be displaced. So that's when a metal in solution is replaced by a more reactive metal. So zinc is more reactive than copper, so we could kick out copper from the copper sulfate. And we could look at the speed at which it displaces, or we could look at other combinations as well. So if a metal is able to displace another metal, that one must be higher than the one it's kicking out, the one it's displacing, or something like that. That's everything I can think of to put in that question. Maybe some diagrams could help, but I'm not going to do that. Just not going to do that. We had to pick up all the marks. We need to have a good answer. So good for 3, reasonable for 2, and limited for 1. I would be confident that's going to pick up all the marks we can get. And that brings us to the end of the question and the end of the paper. Thanks for watching. Goodbye.